A rocky object travels at tens of thousands of miles per hour past Earth. The event creates a sense of global awareness. Cities around the world look up together. This evokes a shared experience. The rocky object is a traveler rushing past our planet. The event is viewed from various cities around the world. Simulated news headlines indicate the detection of an approaching asteroid. The news simulation prompts consideration of the potential danger posed by the asteroid. Viewers are prompted to consider the origin and composition of the approaching asteroid. The simulation highlights the importance of early detection and tracking of near-Earth objects. The simulated news broadcast serves as a reminder of potential cosmic threats. The simulation encourages discussion about planetary defense strategies. The 2025 Sky Calendar presents opportunities for scientific observation. Safe asteroid flybys are featured within the 2025 Sky Calendar. The calendar emphasizes the importance of observing asteroid flybys for scientific research. Detailed information about each flyby event is accessible through the calendar interface. The 2025 Sky Calendar serves as a tool for planning astronomical observation activities. Scientific observation of asteroid flybys contributes to a better understanding of the solar system. Numerous small near-Earth asteroids, NEAs, pass by Earth annually. These asteroids, like 2025 O, typically pass at a safe distance from the planet. The trajectories of NEAs are constantly monitored to assess potential risks. NEAs vary significantly in size, composition, and orbital paths. Advanced tracking systems are used to predict the future paths of these near-Earth objects. NASA's Next 5 Approaches dashboard provides real-time updates on the 5 nearest upcoming asteroid flybys. The dashboard tracks flybys occurring within 4.6 million miles of Earth. This public dashboard promotes transparency by providing continuous, accessible information. The dashboard updates constantly with the latest data on near-Earth object trajectories. The Next 5 Approaches dashboard enhances public awareness of near-Earth objects. The ESA NEO Coordination Center provides a regularly updated list of recent and upcoming close approaches of near-Earth objects, NEOs. This list is updated daily to reflect the latest tracking data and orbital calculations. The NEO Coordination Center's monitoring efforts are part of a global network of observatories and tracking facilities. International collaboration is essential for comprehensive tracking and assessment of NEOs. The ESA NEO Coordination Center contributes to the global effort to identify and assess potential risks from NEOs. The infographic presents the total number of known near-Earth asteroids. A subset of near-Earth asteroids are larger than 1 kilometer in diameter. Another subset of near-Earth asteroids are over 140 meters in diameter. The infographic emphasizes the scale of the near-Earth asteroid population through numerical and visual comparisons. Numerous safe flybys occur, providing significant scientific opportunities. These flybys present no confirmed impact threat to Earth. The simulation visually reinforces the safety of these flyby events. Data acquisition during flybys allows for detailed analysis of celestial objects. Flyby trajectories are carefully calculated to maximize scientific return while ensuring safety. Continuous monitoring and simulation refine our understanding of potential impact risks. Upon discovery of a celestial object, astronomers initiate orbit measurement. Orbital data is then submitted to NASA's CNEOS, Center for Near-Earth Object Studies. Orbital data is also submitted to JPL Asteroid Watch pages. These submissions are part of the process of orbit determination. Orbit determination involves precise calculation and modeling of the object's path. Cosmic distances can be expressed in miles, kilometers, or lunar distances, LD. One lunar distance, 1 LD, is approximately equal to the distance to the Moon. Using lunar distances provides a relatable scale for understanding vast cosmic distances. Expressing cosmic distances in LD offers a more intuitive understanding compared to using miles or kilometers. In media, the term close to describe the distance between celestial bodies can be misleading. What is considered close in space can still equate to millions of miles. The vastness of space requires a different understanding of proximity and scale. Context is crucial when interpreting astronomical distances conveyed by media sources. In 2022, NASA's DART mission intentionally impacted a small asteroid moon named Dimorphos. The DART mission aimed to alter the orbit of Dimorphos around its parent asteroid. This mission served as a real-world test for planetary defense strategies. The impact's success demonstrated the feasibility of kinetic impact as a method of asteroid deflection. Data collected from the DART mission helps refine future planetary defense strategies. The DART mission provides valuable insights into the composition and structure of asteroids. Kinetic impactor's effectiveness is explained by a momentum boost, BONA, T3, greater than 1, resulting from ejected debris. Peer-reviewed results confirm the momentum boost effect, validating the kinetic impactor strategy. The momentum boost is attributed to the mass and velocity of the ejected debris, contributing to the overall change in momentum. Ejected debris amplifies the impact's effect, resulting in a greater change in the target object's trajectory. This momentum boost enhances the efficiency of kinetic impactors in deflecting potentially hazardous objects. NASA's Planetary Defense Coordination Office, PDCO, spearheads U.S. planetary defense initiatives. The PDCO coordinates planetary defense efforts globally. The International Asteroid Warning Network, ION, is a key component of global coordination. PDCO and IAWN work together to detect and track potentially hazardous asteroids. This collaboration aims to protect Earth from potential asteroid impacts. Monthly PDCO updates summarize recent discoveries in planetary defense. These updates also highlight notable flybys of near-Earth objects. PDCO updates include assessments of planetary defense readiness. These summaries emphasize ongoing efforts in planetary defense. The updates ensure stakeholders are informed about the current state of planetary defense. Asteroids are classified based on their orbital characteristics. Reflectivity, or albedo, is a key factor in asteroid classification. Spectra analysis reveals the composition of asteroids, aiding in their classification. Combining orbital data, reflectivity, and spectra provides a comprehensive classification. Asteroid classification helps scientists understand the formation and evolution of the solar system. There is no evidence to suggest that any asteroid observed in 2025 is actually a spacecraft. This statement directly addresses and corrects a common misconception. Scientific analysis confirms the object's natural origin and composition. Misidentification can arise from superficial similarities in shape or trajectory. In 2017, the object Oumuamua sparked considerable interest among astronomers. Oumuamua's unusual characteristics led to speculation, including theories about alien technology. This interstellar object presented a unique case study for understanding celestial bodies from outside our solar system. The object's rapid speed and trajectory indicated an origin outside our solar system. Further research is required to fully understand the nature and origin of interstellar visitors like Oumuamua. Natural explanations such as the outgassing of trapped hydrogen are proposed for the origin of Oumuamua. Research concludes that the data collected on Oumuamua aligns with a natural origin. The hypothesis of trapped hydrogen outgassing explains Oumuamua's unusual acceleration. Alternative explanations involving artificial origins are less supported by the available evidence. Further studies reinforce the conclusion that Oumuamua is a naturally occurring interstellar object. In July 2025, astronomers announced the discovery of interstellar comet 3I, Atlas. 3I. Atlas is classified as an interstellar comet, indicating its origin outside our solar system. The discovery of 3I, Atlas represents a recent advancement in astronomical observation and detection capabilities. Interstellar comets like 3I, Atlas provide valuable insights into the composition and formation of planetary systems beyond our own. Some blogs or influencers have inaccurately framed 3I, Atlas as a mothership. Fact checks and expert sources do not support the mothership claim regarding 3I, Atlas. The inaccurate portrayal of 3I, Atlas as a mothership is an example of misinformation. It is important to verify information from blogs and influencers with credible sources. Misinformation can spread rapidly through online platforms if not properly addressed. Critical evaluation of sources helps prevent the spread of inaccurate information. Currently, there is no verified evidence to support the claim of extraterrestrial life visiting Earth. The question of alien visitation is directly addressed by the lack of empirical proof. Absence of evidence does not equate to evidence of absence regarding extraterrestrial visitation. Scientific scrutiny requires verifiable data to validate claims of extraterrestrial encounters. Unsubstantiated claims of alien visitation lack the rigorous support needed for scientific acceptance. NASA's Bennu samples contain organic molecules and salts. Organic molecules and salts are considered building blocks that may seed life. The Bennu samples do not contain life itself. The presence of organic molecules and salts explains the search for life's ingredients. The analysis of Bennu samples provides insights into the origins of life. Further research on Bennu samples is crucial for understanding the potential for life beyond Earth. The search for extraterrestrial intelligence, SETI, involves continuous monitoring for potential signals from other civilizations. SETI efforts include the search for biosignatures on exoplanets, indicators of potential life beyond Earth. Extraordinary claims of extraterrestrial contact require extraordinary evidence to be considered valid. The scientific community maintains a high standard of proof when evaluating potential evidence of extraterrestrial life. Humans have consistently integrated celestial phenomena into their teachings and moral frameworks. Maori tales feature Tahwiri Matea, the god of storms and winds, embodying the power of cosmic winds. Hindu epics describe vimanas, mythical flying machines, showcasing humanity's ancient fascination with flight and the heavens. These narratives demonstrate a universal human tendency to find meaning and moral lessons in the cosmos. Ancient cultures often used celestial events to explain natural phenomena and impart ethical principles. The integration of celestial themes reflects humanity's enduring quest to understand its place in the universe. Cultural narratives are artistic and symbolic representations, not scientific records. Cultural narratives express values, beliefs, and historical perspectives through storytelling. The distinction between myth and science lies in their approach to truth and evidence. Science relies on empirical observation and experimentation, while cultural narratives rely on interpretation and tradition. Modern ancient astronaut theories propose that extraterrestrial beings guided early human civilizations. Scholars classify ancient astronaut theories as pseudoscience due to a lack of empirical evidence. Pseudoscience lacks the rigorous methodology and empirical support characteristic of genuine scientific inquiry. The absence of verifiable artifacts or data supporting alien intervention undermines the claims of ancient astronaut theorists. Alternative explanations, grounded in archaeological and historical evidence, account for the achievements of early civilizations. Debunking ancient astronaut theories reinforces the importance of critical thinking and evidence-based reasoning. Historical narratives serve as both heritage and inspiration, fostering a connection to the past. Maintaining factual accuracy is crucial for a balanced and respectful understanding of historical events. A balanced perspective requires acknowledging both the positive contributions and the complex realities of historical figures and events. By honoring stories and verifying facts, we cultivate a deeper appreciation for cultural legacies. Combining heritage with clear facts promotes a comprehensive and nuanced understanding of history. NASA and ESA maintain live lists of upcoming close approaches and flybys. These lists highlight safe and scientifically interesting flyby events. These resources provide opportunities for further learning about near-Earth objects. Ongoing flybys in 2025 are tracked and documented for public access. NASA's Lucy mission is currently undertaking a tour of asteroids. The Lucy mission includes a flyby of a main belt asteroid in 2025. This mission highlights ongoing efforts in asteroid exploration. The Lucy mission aims to study the Trojan asteroids, which orbit the Sun in tandem with Jupiter. Lucy's observations will provide insights into the composition and history of these ancient space rocks. Data from the Lucy mission will enhance our understanding of the early solar system. The Lucy mission offers valuable educational opportunities for students. Studying celestial bodies up close enhances understanding of space exploration. The mission's data fosters engagement and inspires interest in scientific discovery. Visual representations of space missions aid in grasping complex scientific concepts. Interactive simulations provide hands-on learning experiences about space exploration. The Lucy mission serves as a perfect example of how we study celestial bodies up close. One lunar distance, 1 LD, is approximately 239.0 miles or 384.0 kilometers. Using lunar distance provides a relatable scale for understanding vast distances in space. The concept of lunar distance simplifies the comprehension of astronomical scales. Lunar distance serves as an intuitive unit for measuring interplanetary space. Understanding lunar distance helps visualize the relative proximity of celestial bodies. Lunar distance offers a human-scale perspective on cosmic distances. Typical flyby distances range from 5 to 20 times the distance between the Earth and the Moon. Many headline-making flybys occur at distances significantly farther than the Moon's orbit. Even so-called close flybys can be more distant than the Moon. Understanding these distances clarifies the scale of flyby events. Verifying numerical data before drawing conclusions promotes informed decision-making. Accurate data analysis mitigates the risk of misinterpreting information and making poor choices. Checking figures ensures that decisions are based on factual evidence, rather than assumptions or estimations. The process of data verification involves confirming the accuracy and reliability of numerical information. Informed decisions, grounded in verified data, lead to more predictable and favorable outcomes. Data validation reduces the potential for errors and inconsistencies in reporting and analysis. An orbit can be physically modeled using common objects to represent celestial bodies. The coin represents the Sun, the marble represents the Earth, and the pea represents an asteroid. This activity demonstrates the relative sizes and positions of celestial bodies in an orbit. Hands-on activities can help visualize abstract astronomical concepts. Flybys often miss due to the vastness of space and the relatively small size of celestial bodies. Even slight deviations in trajectory can lead to significant misses over astronomical distances. The high speeds of celestial objects further amplify the effect of minor trajectory errors. These factors contribute to the low probability of a direct impact during flyby events. NASA's next 5 objects can be selected for comparative analysis. Key attributes such as distance, speed, and size are recorded for the selected object. The Moon serves as a familiar celestial benchmark for comparison. Relative sizes can be visually compared using scaled models. Distance comparisons illustrate the vastness of space. Speed comparisons highlight the relative velocities of celestial objects. Sharing sky stories from diverse cultures fosters cultural exchange and understanding. Sky stories reflect unique cultural interpretations of celestial phenomena. Language diversity enriches the storytelling experience and preserves cultural heritage. Cultural narratives provide a framework for understanding the universe and our place within it. The act of sharing stories builds bridges between cultures and promotes empathy. Sky stories are a powerful tool for education and cultural preservation. Sky stories encourage thoughtful reflection on universal themes. Reflection on sky stories can reveal insights into natural cycles and human experiences. The sky serves as a canvas for interpreting patterns and deriving meaning. Analyzing sky patterns can lead to a deeper understanding of time and change. Wisdom is gained by contemplating the sky's constant yet ever-changing nature. Sky stories provide a framework for philosophical contemplation and personal growth. The initial step in addressing a potential threat involves precise discovery and tracking. CNEOCC, Center for Near-Earth Object Studies, and ION, International Asteroid Warning Network, are utilized for this purpose. Precise tracking is essential to determine the object's trajectory and assess the level of threat. This process is initiated upon identifying a real threat. The decision-making process culminates in a globally agreed-upon course of action. This global decision represents a unified strategy for addressing a specific challenge or opportunity. Effective global decisions require comprehensive data analysis and collaborative input from various stakeholders. The agreed-upon course of action is then implemented across different regions, with adjustments made as needed. Deflection methods involve altering the trajectory of an object well in advance of a potential impact. Kinetic impact is one tested method for deflecting potentially hazardous objects. The DART mission serves as an example of kinetic impact deflection. Early deflection is crucial for effective trajectory alteration. Planetary defense technologies have undergone rigorous testing to validate their effectiveness. The reality of planetary defense is underscored by successful technology validation. Validated planetary defense systems are no longer confined to the realm of science fiction. Rigorous testing confirms the viability and reliability of planetary defense strategies. The transition from theoretical concepts to tested and proven planetary defense technologies marks a significant advancement. There is no evidence to suggest that the asteroid is a spaceship. The object identified as the 2025 asteroid is a naturally occurring celestial body. Scientific analysis confirms the asteroid's composition aligns with known geological materials. The asteroid's trajectory and velocity are consistent with natural orbital mechanics. Asteroids frequently pass near Earth. These asteroid visits are generally safe. The constant visits of asteroids pose minimal threat. Monitoring systems track near-Earth asteroids. Advanced technology ensures Earth's protection from potential asteroid impacts. The question of whether we are alone remains unanswered. Each space exploration mission brings us closer to finding potential answers. Flyby missions provide valuable data for understanding extraterrestrial environments. Sample collection is crucial for analyzing potential signs of life. Data analysis from these missions helps refine our understanding of life's possibilities. Future missions hold the key to unlocking the secrets of the universe and our place within it. Maintaining an open mind involves actively considering new ideas and perspectives. Open-mindedness fosters creativity and innovation by encouraging exploration of unconventional solutions. Encouragement plays a crucial role in promoting open-mindedness by creating a supportive environment for sharing ideas. An open mind facilitates continuous learning and adaptation in a constantly evolving world. Maintaining a kind heart fosters positive interactions and relationships. Kindness promotes empathy, understanding, and compassion towards others. Encouragement provides support and motivation, fostering personal growth and resilience. Practicing kindness and offering encouragement creates a supportive and uplifting environment. Kindness and encouragement, when combined, amplify positive impacts on individuals and communities. Verifying information ensures accuracy and prevents the spread of misinformation. Reliable sources and cross-referencing are essential components of effective fact-checking. Maintaining a commitment to accuracy builds trust and credibility in reporting and communication. Encouragement promotes a culture of continuous improvement in fact-checking practices. The Earth and Moon are separated by a vast distance, dwarfing the size of near-Earth asteroids. Near-Earth asteroids, despite their potential impact risk, are relatively small compared to the Earth. The immense distances in space highlight the low probability of asteroid impacts on Earth. Visualizing the scale of space helps to understand the relative sizes and distances of celestial bodies. Asteroids are composed of a mixture of rocks, metals, and organic compounds. The proportion of rocks in asteroids varies depending on the asteroid type and its formation location. Metallic components of asteroids include iron, nickel, and other trace metals. Organic compounds found in asteroids can include carbonaceous materials and complex molecules. The composition of an asteroid provides insights into the early solar system's formation and evolution. Analyzing asteroid composition helps scientists understand the building blocks of planets. Impact craters form on planetary surfaces due to collisions with asteroids. The kinetic energy of the asteroid is transferred upon impact, creating an explosion and excavating material. Ejected material forms a raised rim around the newly formed crater. The size and shape of the crater depend on the asteroid's size, speed, and angle of impact. Impact craters provide insights into the geological history of a planetary surface. Astronomers use telescopes to observe and track asteroids. Telescopic observation is a key method for monitoring near-Earth objects. Tracking asteroids requires precise measurements and continuous observation. The effort involved in monitoring near-Earth objects is significant. Advanced technology is essential for detecting and analyzing asteroid data. Scientists predict asteroid orbits using complex mathematical models and observational data. The graph visually represents the predicted path of an asteroid over time. Orbit prediction involves calculating the gravitational influences of various celestial bodies. Accurate orbit prediction is crucial for planetary defense and space exploration missions. Uncertainties in observational data can affect the accuracy of long-term orbit predictions. Asteroids burn up upon entering Earth's atmosphere due to intense friction. The friction-induced burning creates a bright meteor effect. This process prevents most asteroids from reaching the Earth's surface. Atmospheric entry serves as a natural defense mechanism against space debris. Space debris includes both natural asteroids and man-made objects orbiting Earth. Man-made space debris consists of defunct satellites, rocket parts, and fragments from collisions. Natural asteroids are rocky remnants from the solar system's formation. The distribution of space debris varies by altitude and orbital inclination. Tracking and cataloging space debris is crucial for collision avoidance. Mitigation strategies aim to reduce the creation of new space debris. The lunar distance can be visualized through comparisons with familiar terrestrial scales. Illustrative examples help to contextualize the vastness of the distance between the Earth and the Moon. Visual analogies provide an intuitive understanding of the lunar distance. Infographics effectively communicate the scale of astronomical distances using relatable references. The asteroid belt is located between the orbits of Mars and Jupiter. Asteroids within the belt vary greatly in size, from a few meters to hundreds of kilometers in diameter. The asteroid belt is composed of a vast number of irregularly shaped rocky and metallic objects. Gravitational perturbations from Jupiter prevent asteroids from coalescing into a planet. Collisions within the asteroid belt can fragment asteroids, creating smaller debris and dust. Some asteroids are ejected from the belt due to gravitational interactions, becoming near-Earth objects. The Sun's gravitational pull significantly influences the orbits of asteroids in the solar system. Planetary gravitational forces also contribute to the perturbation of asteroid orbits. These gravitational interactions can cause asteroids to cross Earth's orbital path. Orbital resonances with planets can lead to increased eccentricity in asteroid orbits. The cumulative effect of these gravitational forces leads to complex and unpredictable asteroid trajectories. Asteroid mining aims to extract valuable resources from asteroids, including metals, water, and rare elements. These resources can be used for in-space manufacturing, propellant production, and supporting deep space exploration. Robotic mining vehicles and automated systems are essential for efficient resource extraction in the harsh asteroid environment. Extracted resources are processed and refined on-site, using advanced technologies to produce usable materials. Processed materials are transported to orbital facilities or spacecraft for further use or delivery back to Earth. Asteroid mining offers a potential solution to resource scarcity and enables sustainable space exploration. Planetary defense strategies aim to deflect asteroids that pose a threat to Earth. The gravitational tractor method uses the gravitational pull of a spacecraft to slowly alter an asteroid's trajectory. Kinetic impact involves directly colliding a spacecraft with an asteroid to change its course. Laser ablation utilizes high-powered lasers to vaporize the surface of an asteroid, creating thrust that pushes it off course. Nuclear detonation, as a last resort, can be used to vaporize or fragment an asteroid. Near-Earth objects, NEOs, are celestial bodies whose orbits bring them into proximity with Earth. These objects include asteroids and comets with sizes ranging from small rocks to several kilometers in diameter. An NEO's orbit must bring it within a certain distance of Earth's orbit to be classified as such. Understanding NEOs is crucial for planetary defense and assessing potential impact risks. Orbital parameters, such as semi-major axis and eccentricity, determine whether an object is classified as a NEO. NEOs are continuously monitored and tracked by observatories and space agencies worldwide. The kinetic impactor method involves altering an asteroid's trajectory through a high-speed collision with a spacecraft. A spacecraft is deliberately crashed into an asteroid at high velocity to change its momentum. The transfer of kinetic energy from the spacecraft to the asteroid results in a change in the asteroid's orbital path. The magnitude of the trajectory change depends on the spacecraft's mass and velocity at the time of impact. This method provides a means of planetary defense by deflecting potentially hazardous asteroids away from Earth. Precise calculations and navigation are essential for a successful kinetic impactor mission. A gravitational tractor uses a spacecraft's own gravity to alter an asteroid's trajectory. The spacecraft applies a continuous, gentle gravitational pull to slowly nudge the asteroid. Over time, this small but persistent force gradually changes the asteroid's course. The gravitational tractor method provides a controlled and predictable means of asteroid deflection. This technique can be used to prevent potential asteroid impacts with Earth. Laser ablation uses high-powered lasers to vaporize material from an asteroid's surface. The vaporization of material generates thrust, altering the asteroid's trajectory. The amount of material vaporized directly influences the magnitude of the thrust. Precise control of the laser allows for fine-tuning of the asteroid's path. Laser ablation provides a non-contact method for asteroid deflection. This method can be used to prevent potential Earth impacts. Nuclear deflection is a method to potentially alter the trajectory of celestial objects. This method involves using nuclear explosions to impart a force on the object, changing its course. The effectiveness of nuclear deflection depends on the size and composition of the celestial object. International concerns and regulations govern the use of nuclear devices in space. International collaboration is crucial for effective planetary defense against potential asteroid threats. Joint missions enable resource pooling and shared expertise in planetary defense initiatives. Data sharing between space agencies enhances the accuracy of asteroid tracking and trajectory prediction. Collaborative research accelerates the development of advanced planetary defense technologies. Joint simulations and exercises improve preparedness for potential impact scenarios. International cooperation ensures a coordinated global response to protect Earth from cosmic hazards. Risk assessment for near-Earth objects involves evaluating potential impact threats. Object size is a critical factor in determining the severity of a potential impact event. Velocity significantly influences the kinetic energy and destructive potential of near-Earth objects. The probability of impact is a key element in assessing overall risk. Risk assessment combines size, velocity, and probability to quantify potential threat levels. Comprehensive risk assessment informs mitigation strategies and planetary defense efforts. An asteroid impact can cause significant regional damage depending on its size and impact location. Global climate effects, such as dust clouds blocking sunlight, are a potential consequence of large asteroid impacts. Long-term environmental changes, including altered ecosystems and species extinction, can result from asteroid impacts. The severity of impact consequences is correlated with the asteroid's size, velocity, and composition. Simulations help scientists understand and predict the potential consequences of asteroid impacts. Early detection is crucial for effective planetary defense against potential asteroid or comet impacts. Advanced telescopes and monitoring systems are essential for identifying potential threats as early as possible. Early identification allows for more time to develop and implement mitigation strategies. Mitigation strategies may include deflecting or destroying potentially hazardous objects before they reach Earth. Global collaboration and data sharing are vital for comprehensive planetary defense. Public education plays a crucial role in planetary defense by informing citizens about potential asteroid threats. Encouraging citizen scientists to participate in asteroid searches enhances data collection and analysis efforts. Citizen scientists contribute by identifying potential asteroids in astronomical images. Raising public awareness increases support for funding planetary defense programs. Planetary defense programs aim to detect, track, and potentially deflect asteroids that pose a threat to Earth. Increased funding enables the development of advanced technologies for planetary defense. Common myths about asteroids often involve sensational claims lacking scientific basis. Scientific reality portrays asteroids as diverse celestial bodies with varying compositions and trajectories. Asteroid impact risks are statistically low, but ongoing monitoring and research efforts are crucial. Asteroids are not just threats, they also represent potential resources and scientific opportunities. Accurate information and scientific understanding are essential for debunking myths and promoting informed perspectives on asteroids. Future missions are planned to study asteroids, enhancing our understanding of these celestial bodies. Sample return missions aim to collect and bring back asteroid material for in-depth analysis. Flyby missions involve spacecraft passing by asteroids to gather data through remote sensing. These missions contribute to ongoing efforts to learn more about the composition and origin of asteroids. Studying asteroids can provide insights into the early solar system and the formation of planets. Data from these missions will improve our ability to predict and potentially mitigate asteroid impacts on Earth. The origins of asteroids remain a significant area of ongoing scientific investigation. The precise composition of many asteroids is still not fully understood, presenting challenges for resource assessment. The potential for asteroids to contain the building blocks of life is an open and actively researched question. Further scientific inquiry is essential to unravel the mysteries surrounding asteroids and their role in the solar system. Staying informed about asteroid research is crucial for understanding potential threats and opportunities in our solar system. Supporting planetary defense efforts contributes to the safety and security of Earth from potential asteroid impacts. Appreciating the wonders of the cosmos fosters a sense of curiosity and responsibility towards our place in the universe. Engaging with scientific advancements helps humanity prepare for and mitigate potential risks from space. Cultivating a sense of responsibility encourages proactive involvement in protecting our planet and exploring the universe.